Alrighty team, so we're going to be looking at our first two ways to represent a plane with equations using vectors. So we're going to look at the vector equations of a plane and then the parametric equations of a plane. So we have these versions for lines. We're going to see what the planar versions are going to look like. So a plane, again, is a two-dimensional flat surface in 3 space. So if I have my axes here, however you want to label them, we've talked about the xy plane. That was that flat surface that connects the x and y axis. We've talked about the yz, the xz planes. Those are all two-dimensional flat surfaces. What we're going to do is we're going to now be able to make any kind of plane. So no matter how slanty, it doesn't have to be horizontal, it doesn't have to be vertical. We're going to get the equation of any plane. So I'm going to try and draw a picture of a plane here, and we'll see how well I can do. Okay. Maybe something like that. Or no, I want to go back here. Something like that. Now that doesn't have much depth to it. I extend my x-axis out a bit. How do I want to draw that? No, like that's fine. So that I really have no idea where that is compared to my axes. So I'm going to see if I can give it some kind of depth here. I'm just kind of experimenting. So if I imagine where that plane is piercing the xy axes, and then so that part of the axis is in behind, and that part of the axis is in behind, and that part of the axis is in behind. Does that kind of give us a bit more depth? I'm not sure if it does or not, but I'm going to go with it. So you can kind of maybe picture this tortilla chip sitting above the axes there, and then the plane extending forever and ever and ever beyond that. Okay. Maybe that works, maybe that doesn't. I'm going to show you a better picture later made by a computer, not by me. So we're going to tackle this equation of a plane the same way that we tackled the equation of a line. So what we're going to do is we're going to have some point that is sitting on the plane, some initial point, x naught, y naught, and z naught. And then if we wanted to define a line, we would take some vector that points that way along the plane. That's how we did it before. That's how we did the equation of a line. Sorry, we had one direction vector that's somewhere lying on that plane, so not sticking off that page, that's kind of floating through space, kind of continuing to go further and further and further. If I do that, does that look better? I don't know. It makes sense to me. Okay. So, one direction vector. If I only could stretch that one vector, I could only find other points lined up along that line that defines. So if we want to be able to have sort of 2 dimensions to go both ways on the surface, we're going to need a second vector. So maybe a vector pointing up this way that's also lying on that one. I'm going to call that one capital D. Sorry, I labeled them with ones, but I think I just want capital and lowercase is how I did it on the note. Or on the formula sheet, I mean. So if we have 2 direction vectors, then if I wanted to get to, say, a point way over here, I could start at that starting point. I could do some stretch of that vector going back that way. Probably need to go a bit further. And then another stretch of this vector, maybe backwards in that way. And that could land on another point on the plane. So what we're getting at is any point on the plane, x, y, z, is going to be starting at some starting point. We're going to stretch our first direction vector by something, and stretch our second direction vector by something. And so t and k have to be our real numbers. So we need 2 different variables here, because the amount that I stretch the purple vector is different than the amount I stretch the green vector in my picture. Okay, so any point on plane, this is a starting point, and again that could be any of the points on this plane. And the direction vectors could be any two arrows that sit on that plane, that don't leave that plane. As long as they're pointing different directions, we'll be able to turn and go to all the other points. So direction vector 1 and direction vector 2 are there and there. And what I kind of want to focus in on is this handy dandy thing. We've got a name for that. We've got a linear combination of the two direction vectors. So we've got a starting point plus some linear combination of two direction vectors. And so those two direction vectors, they're forming kind of the basis for our plane. We can take those and stretch them and combine them to make any other place on that plane, any other vector that stretches along that plane. So if I add that and that, that's how I'm getting this kind of shortcut to go from my starting point to there. There's my linear combination vector there. And I've got more pictures of this later. That's maybe going to show it first. So if I want to write that out kind of in full, x, y, z is some x naught, y naught, z naught plus t times d1, d2, d3 plus k times capital D1, capital D2, capital D3. So that's going to be the vector equation of the plane. And guess what? If we want our parametrics, we're going to do exactly what we've done before. X naught plus D1 times t plus D2 times k. Y is going to equal y naught plus D2 times t plus, this is capital D1, sorry, capital D2 times k. And z is going to be z naught plus little d3 times t plus big D3 times k. Whew. Okay. So what I'm going to have you do now is I'm going to give you one problem that you're going to work on. You can work on it with group mates on the board if you want. And then I want you to come back to the video. I'm going to show you a solution to that problem, but I've also spent, over an hour of my Saturday messing around on Desmos, because I remember Desmos just introduced 3D graphing. So I've got a pretty picture that I want to kind of demonstrate what I'm trying to show with my hand-drawn picture quite a bit better. So the problem you're going to work on first is we have 3 points, A, B, and C, and I would like you to find the vector equation of a plane that contains those 3 points. So go ahead and pause the video there and work on that, and then I will show you a solution when you unpause. Okay. So if we're going to do this, our equation's going to look like this. Some starting point plus t times a direction vector and k times yet another direction vector. And what we have, somewhere there's an A, somewhere there's a B, and somewhere there's a C sitting on our plane that exists somewhere. And so for starting point, we have 3 valid choices. I'm going to choose A, because it's the first one. Now, to get our direction vectors, we have a couple choices here. So simply, we can't use B, we can't use C, because those are points on the plane, they're not directions on the plane. I hope that you quickly realize that if you make, say, the vectors A, B, that would be a direction vector on the plane. And maybe AC would be another one. I could also use CB, that would be totally fine. The only thing you can't do if you use AC, then you can't use CA. They have to be going different directions, but any 2 combinations of those points that are pointing different directions would work perfectly fine. So AC is going to be C, take away A, so that's going to be -3 to -1, something like that. And AB is going to be B, take away A, that's going to be 1, -3, 4, I believe. So I'm going to fill those in as my two direction vectors. There we go, and there's my vector equation of that plane. I'm going to remember to say, hey, these two variables I introduced, they can be any real number, and if we cycle through every real number, we're going to get every point on that plane. So I'm going to have a follow-up challenge involving this plane, but what I want to do is switch over, because like I said, I remembered when I was on Desmos last, they said, hey, we've got 3D graphing now. So I went and I checked that out. So here we go. Oops. Looking at the wrong screen. Okay, so to get here, all you have to do is, whoops, is that going to work for me? No, of course not. Oh, that's what I want to try and do. Sorry, I'm not recording my full screen. But if you just do desmos.com/3D, you'll get to the 3D calculator mode. Here we go. So you can see I spent much time making this. So we've got our 3 points, and those 3 points all lie on the same plane. There's a flat surface that connects them all, and there it is. There's my flat surface that's connecting those 3 points. We needed to make 2 direction vectors, so we connected A to B and A to C, kind of like that. I'm going to get rid of those 2 points. So these are the things we're using to define the entire plane. We've got that single point, that orange thing in the middle, and then one vector pointing that way, one vector pointing that way, and they all live on this flat surface. One thing I'll point out about Desmos is it will graph basically a rectangle, or a cube, I should say, rectangular prism, so you can define how far it wants it to show. But anything that goes beyond those boundaries will kind of get cut off. That's why there's this weird slant, because it's going outside of the box that they're drawing on. So that's hitting that edge of the box there. Okay. Yeah. So those 2 vectors and that point are enough to define every other point on the plane. And so when we take the starting point and stretch it by that red vector, what we're really doing is we're making, oh, that's the blue one. We're making an entire line, right? If I just had the point plus a stretch of that vector, I would get an entire line. That's the equation we were making yesterday. And then ditto with these. Ooh, it kind of spins if you stop touching it. Okay, so ditto with the blue. If I stretch that blue vector in both directions as much as I possibly can, I'd get all the points along that line. And what I've always tried to draw on the board, and I tried to do it when we did linear combinations, is you can kind of think of those 2 vectors as defining 2 axes. So you can kind of think of this red and blue line as being these new set of axes we're using to represent all the other points on this plane. And by that, I mean we could kind of make this parallelogram-shaped grid. And yes, I did have to enter every single line as its own equation on this grid, and that's why I'm saying I spent over an hour of my Saturday morning making this wonderful picture for you. There's our beautiful parallelogram-shaped grid using those 2 vectors that all lies on that plane. And let's say, scroll down, I wanted to get to that point that's also on the plane. Well, in order to do that, I would start at my starting point, the orange point that's kind of my origin between those axes, and maybe I would stretch that red vector we started with, stretch it that much, and then add on that blue vector, kind of stretch that much, and I would end up at that other point on the plane. And you can kind of see, if to get to any other point, you could kind of follow these grid lines in the exact same way. And even if that point wasn't as nice as that one I just made up and landed somewhere else, kind of between the grid lines. Hang on, I'm going to have to turn that off and that off. I would just have to stretch those vectors by a fractional amount to get to that point. There we go. And that's how we can get to any other point on the plane, by using a starting point and two directions. This little red one in here and that little blue one in there is what we started with. And it doesn't matter what this parallelogram looks like if they were pointing different directions. As long as they stayed on this flat surface, I'd get a whole new grid that I could use to represent that same plane. Ooh, there we go. Isn't that fancy? Okay, so I have not chosen which one I want to do. But my last challenge, okay. So my picture's kind of cut off. I could kind of see the y-intercept of the plane there, where the y-axis is sitting in the plane, but because I've not asked Desmos to go up high enough, I can't see where the z-intercept is. So my last challenge, and I don't know how ugly this is going to get, but I'll solve it after you try and solve it. My last challenge is I want you to use your equation, see if you can find the z-intercept of this plane. Where does this plane intercept that z-axis way up above? Again, you can pause. I'm going to solve it, see how gross this gets, and then we will meet back. Okay, so if I want to find a z-intercept, that means that the point is going to look like 0 for x, 0 for y, some number for z. So what I might do is take my parametric equations from that plane that we've already found. I believe that's the parametric for x, and I'm going to set it equal to 0. All right, and then my y equation, since we know y is also 0, my y equation is going to look like 0 equals 4 plus 2t minus 3k. So here's my two equations that we're working with. And I need to find the t and k that make that happen. So, again, two equations, two unknowns. This is just that linear combination question again. So what we're going to do is choose one of them to solve for a variable. Hey, I'm going to choose the first one and solve for k, because that looks pretty darn easy. So that first one tells me k is 1 plus 3t. And I'm going to plop that into the second one. I'm going to take this, plop it into that equation. And I'm going to get 0 equals 4 plus 2t minus 3 times 1 plus 3t. And I'm going to get 0 equals 4 plus 2t minus 3 minus 9t. So that's going to be 1 when I combine the 4 and the minus 3. When I bring it over, it's going to be negative 1. When I combine those t's, I'm going to get negative 7t. And this is what I meant. I didn't know if it was going to be nice, and obviously it's not nice. T is 1/7. So with t being 1/7, k is going to be 1 plus 3 times a 7th, which is going to be 7/7 is 1, 3/7 is 3 times a 7th, 10/7. Okay, that's gross. Now my z-intercept, I've got my t, I've got my k, I've just got to plug that into the full equation, and I should be able to get the z that goes with it. So, in fact, I could just grab the z, because we know, if I did that right, that the x and y are both 0. Now let's plug it into the whole equation just to confirm. X, y, z should equal minus 1, 4, 5, am I remembering that right? Plus t is 1/7. That vector is negative 3, 2, 1, negative 3, 2, 1, plus k was supposed to be 10/7. 10/7 times that last vector, sorry for the scrolling, 1, negative 3, 4. Okay. So, I'm going to change everything to 7ths to make this my life easier. So in this first one, that's going to be negative 7/7. That's going to be 28/7, and that's going to be 35/7. If I multiply that 1/7 through, I get negative 3, I get 2/7 and 1 more 7th. And then if I multiply the 10/7 through, I'm going to get 10/7. negative 30 over 7 and 40 over 7. And here's where I should have done this beforehand to make sure. But if I add up my x's, negative 7 over 7, negative 3 over 7, 10 over 7, those do in fact make 0. Whew. Ooh, 28 and 2 is 30, minus 30. Those do in fact make 0. I didn't mess it up. 35 and 1 is 36, plus 40 is 76 over 7. There is my z-intercept of that plane. Woo! I could go back in Desmos and graph it, and we could see it's on that plane, but I think we've had enough for today. So, there's my beautiful lesson. You can attempt to solve that exit card, but attempt to solve the exit card. You're going to do that. I will solve it in the video as well. So again, you can pause, and then the last part of this will be me solving this exit card. Okay, so we have a plane. And that plane is perpendicular to another plane. So we're going to be finding the equation of the red plane. We have this other plane that is the blue plane. That's the equation we were given. Something like that. Beautiful. And these two things, that's a 90-degree angle there. Whew. Oh my goodness. Okay. Find the vector and parametric equation of the plane that's perpendicular to that blue plane. And our plane contains that line. So that line here, let's say, is some line sitting on the red plane. Okay, so that means this is a point on our plane, because that whole line's on the plane. That means this direction vector is a direction vector on our plane. So our plane is 2/3 done. We can use this for our starting point, and that for our first direction vector. Now, maybe this picture isn't as useful as I thought it was going to be, but that blue plane, what we know about it is we know two vectors on that blue plane. Maybe I'll draw those in blue. Those are the two direction vectors here and here. Now, that blue plane is perpendicular to our plane. So, maybe I'll draw the side view. There's the blue plane, and there's our plane. If I take those two direction vectors that are sitting flat on the blue plane, and I do their cross product, I will get a vector perpendicular to those two vectors on the blue plane. And that vector that's perpendicular to those vectors on the blue plane will also be landing on our plane. So the cross product of those two direction vectors is going to be a direction vector for this new plane we're making. So I'm going to call that the normal vector for the blue plane. So the normal vector for the blue plane is going to be that crossed with this. Dun, 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 dun. I don't know why I keep making that sound. That, this. So I get negative 16, subtract 18, that's negative 34, I believe. I'm going to get 6, subtract 8, that's negative 2. And I'm going to get negative 6, subtract 4, that's negative 10. So in theory, that's my cross product. If I check it, say with this one, I'm going to get negative 34 times 1. I'm doing the second vector. Negative 2 times 3 is 6, and negative 4 times negative 10 is 40. That didn't work. Oh, because that's negative 6. Negative 2 times 3 is negative 6. So I do have a dot product of 0. There's my quick check that I did that cross product right. And again, that cross product is sticking perpendicularly out of that blue plane, and since our plane is perpendicular to that plane, well then that's going to lie along our plane, so we can use that for our second direction vector, -34, -2, -10. And let's say I didn't like that vector for whatever reason. Remember, any scalar multiple is also the same, also has the same direction. So if I wanted, I could scale that one down, say divide it by -2 and get 17, 1, 5. Then I wouldn't have all those negatives to deal with. You don't have to do that, but it's also the same. So there's my vector equation, and then it asks for both types, so here's my parametrics coming out really quick. For no t's in that one, so I can just leave it off and do 5k. I kind of like to space it out though, so I don't get confused. 6 plus 2t, and then, see, I did get confused. 1k for the y's, 5k's is the z. There's my parametric equations. Woohoo! Okay, and there we have it. There's my probably too long video, but I hope you stuck it out.